My name is Veronika, and my topic is how knowledge distillation inspires foundational models creation. And as many data scientists here, okay, no worries, everything will be pretty high level, and we will uncover all the details of the knowledge distillation and foundational models, and everything will be pretty clear. So let's start, and I like to start with a challenge, and I will talk a bit about challenges for model serving. First of all, there are two most typical ways how we can serve the model. The first one is model as a service. Basically, we provide an API to the users, and they can trigger it to get the results from our model. And we usually host models in clouds. And we face the problem of pretty pricey GPUs. And as the models are only getting bigger nowadays, the prices for GPUs are pretty huge and costly. And another way how we can serve our model is to place it directly on an edge device. And it's the most typical case for some photo editing apps. And here we face a problem of limited hardware resources. Another problem for model serving is latency and throughput of our model. It's basically model response time, and we're all striving for real-time predictions. And again, it can be very hard, especially when we are serving large models. And the last challenge, which is actually the root causes for all the challenges above, is the model size. And as already mentioned, models are getting only bigger nowadays, and it affects everything. It affects how much GPU memory you need, how powerful your GPU should be. So it's a very crucial problem. And there is one special technique called knowledge distillation that will help you to reduce the size of your model, but preserve its original accuracy. And it works actually pretty simple. You just take your large model, which we call a teacher, and we try to transfer all the knowledges to a student model. So the training approach is pretty simple. We have our data, we feed it to our teacher model, which is frozen, and we feed it to our student model. And we train student model in a way that it will replicate outputs of a teacher. And you can, of course, ask, like, why not just to take that small model and train it on our data? First of all, when we train those large models, we have a lot of data. And those models, large models, can capture all of the insights and details of your data because of their sizes. While when you're working with a small model, you have some limitations of your data set size. But when we are using knowledge distillation, we will be able to transfer all the wisdom, let's say, of a teacher to a student model because we are using soft targets. Let's take, for example, classification task. We usually have an image and a tag attached to it. And when we are training the model, we want our model outputs match that one specific label. And it's pretty hard option, while in knowledge distillation we use soft approach because we are trying to match output probabilities of a teacher, which actually a probability of any class to occur in an image that is given right now. So that way we can transfer all the insights of the teacher to our student model. And that technique is especially helpful nowadays because we are in the era of foundational models. And what are those? Foundational models are very big models that are trained on a huge data sets, and they have the following features like multitasking. Those models can solve many tasks across many different domains, and it's pretty useful because we are shifting right now in data science, from having a task-specific model to a model that is very capable, so it can be applied to many tasks in your company, on your project. And another very important feature of all foundational models is their generalization capability. And generalization capability is an ability of a model to work great on specific data. Basically on the data that model probably hasn't seen during training. And I will show you a very nice example of generalization capability. So I decided to run a classification task on very specific images from telecommunication domain. And I took 2 models for my experiments. On the left, you can see the results of efficient net model. That is a very good model, but it requires fine-tuning on your data. And on the right, you can check out the results for foundational model. And you specifically should check F-score metric, which is a pretty typical metric in computer vision to measure the accuracy of your classification models. The better the F-score, the better the performance of your model. And you can see that the results between efficient net, which I promise you is a very good model, and foundational model. And as a foundational model, in this example, I took DINOv2. And surprisingly, DINOv2 was inspired by knowledge distillation while it was creating. So Dino model is a model that was released by Meta AI more than a year ago, and they claim that this model is the first foundational model in computer vision. And I partly agree with them, because we already seen the generalization capability of a Dino model, which means that we can use it out of the box. Like imagine you can skip all the steps like gathering data set, researching architectures, training your models, and testing them by just taking a large foundational model. And very exceptional feature of DINOv2 is better pixel level understanding. What is pixel level understanding? Is the ability of a model to capture not just objects in your images or in your data, but the interaction between those objects, part of the objects, and it's really important and pretty rare. So what was their method? As I already told you, it is revolved around knowledge distillation, and they also got inspired by some research in NLP field. And in NLP, there were some papers when they took pretty large transformers, and they trained those large transformers without any labels. And guys from Meta decided to try this approach in computer vision. Of course, there are some challenges to replicate the experiment from NLP in computer vision and vice versa, but we won't dig into them today. So they decided to take vision transformers, and they also decided to use self-supervision, which is approach in computer vision when you don't use any labels. And they got the Dino method. And you can see that it's really similar to the knowledge distillation approach. We have 2 models. We have the same data which we are feeding through those models, and in the end we want the output probabilities to match, but there are some differences that I will cover. So first of all, we have our data, and we apply augmentations to the data. Augmentations is a really cool technique in data science that helps you to make your data a bit different each epoch by applying some basic transforms. And they apply different set of augmentations to the images that are going to different networks. The next difference from knowledge distillation is the models, because they are the same size. While in classical knowledge distillation, student model is much smaller than the teacher. And they are both training, but they train in a different manner, and I will cover it later. And they still training the models in a way that their probabilities would match. And remember how I told you about amazing pixel level understanding? That's how they achieved it. They were using this different set of augmentations, and for images that were going through the student model, they were cutting most part of an image, leaving only 30–40% of it, that called local crops. And for the teacher model, they were leaving 70–80% of the whole image. And by utilizing that approach, they enforce that local to global correspondence, because imagine such a different views of an image that are going through 2 separate networks, and then they want these features to match. And also about that differences in a training approach for teacher and for student. Student model is being updated each iteration, while teacher model is being updated only once in a while and based on the previous iterations of your student. It's like teacher, and you can see it like on this plot, teacher is always a bit better than a student. Teacher is being updated, taking into account all the mistakes of a student because it takes an average of student past updates. And they actually tried a lot of different approaches how they would update a teacher model. They tried to copy a student, they tried to use previous iteration of a student, and only previous epoch started to work. And that approach of taking average snapshots of a student was the best, and it's called momentum. And this is the whole Dino method. It was actually introduced earlier than the DINOv2 model. And in that paper where they introduced Dino method, they promised that they will take even larger transformer, giant one, and they will train it on a large set of uncurated images. And that's how DINOv2 was born. They actually made data set bigger, but they curated it, and it was a really nice pipeline that I will share with you. And they left the whole Dino method as it was, but they did some improvements in self-pre-training. They did some stuff to optimize the training because they were training giant transformer, which required a lot of memory, so they needed to do some implementations so that their model won't cost billions of dollars to train. And about the data set, they actually introduced a really cool pipeline by using their own framework from Meta. So they did massive curl of data from the web. They downloaded like more than 1 billion of images. They applied some basic cleaning techniques like PCA hash deduplication, not safe for work filtering, face blurring, and so on. And then they came up with an honestly amazing approach using FICE library. FICE library is a library by Meta AI that will help you to find the data samples that are really similar to your anchor sample very fast. It's written in C, it's open sourced, so it's pretty good library, you can check it out. And the approach was the following. They had their uncurated data, and they have some curated data, of course, because there are many open source data sets that you can use while training your models. And they were taking one sample from that curated data, and they were looking for similar images from the uncurated pool. They were deduplicated them, and then they were adding them to a final data set. And fun fact, they collected that data set and filter it from more than 1 billion images to 142 in 3 days. And they were running that pipeline on a very massive set of GPUs. And just gathering the data costed them more than $500,000. As I already told you, they left the original Dino method where we have knowledge distillation when we are trying to match output probabilities. You can see how it looks in Python, the updating of a teacher using past snapshots of a student. Another cool technique that they introduced in DINOv2 is a way how you can use scheduling of resolutions to reduce training time, but enables that accuracy that comes with high resolution images. So let me explain you. There are different types of tasks in computer vision, and we have segmentation and depth estimation tasks. And those tasks, to be very accurate and very perfect, they require high resolution images. But training on high resolution images is long and costly because bigger data requires bigger GPU memory and more powers. So they introduced a scheduling of resolution. They were training the Dino the whole way with lower resolution images, and only on the last couple of iterations they increased the resolution of an images. And you can see the results. On the left we have classification data sets, and on the right the results for segmentation data sets. The yellow line is lower resolution images all the way, the pink one high resolution images all the way. and the blue one is scheduling approach. And you can see that it's pretty close in performance to the perfect one, higher resolution images, but they saved a lot of time, thus money, which is pretty cool. An even cooler thing is, as I already told you, they were training the giant transformer, but they provide actually a set of DINOv2 models in different sizes. And they trained with their approach just one giant transformer, sorry. And all the other transformers in smaller sizes, they actually distilled using classical knowledge distillation approaches. And you can see the plot, which is actually my favorite one. There are results for the model across different benchmarks and different data sets. And you can see the red one is the results for our giant transformer, which is, of course, very good. And the orange one is the results of a smaller model that was distilled from the giant transformer. And you can see that results are pretty close to the original model, sometimes even outperforms it, which is pretty massive in my opinion. And they also did try to train that smaller model from scratch utilizing the Dino approach. And you can see the results in the blue one, and they're worse than the results for the giant original model and even for distilled one. So knowledge distillation, well, it's just to prove that knowledge distillation can help you to achieve better results when you're distilling from larger models rather than training them from scratch. And we can, of course, check out the benchmarks. The benchmarks is actually something that comes with every data science paper. It's like a place where the researchers just showing that their model is much cooler in performance to the others on representative benchmarks. And here, I want you to pay attention to the results for Dino model in comparison to the CLIP one. CLIP one is also a very cool model in computer vision, but it requires some labeling. And I think here, the performance is the same, but the most thing here that the authors try to show is that model without any labels can achieve the same results as models that were trained using labeled data. And there is like the talk in data science right now that actually this strict labels, it's something that prevents the model to learn more. Because actually imagine a picture of a dog running on the grass. We would basically mark it as dog, but we are losing all that information that dog is running and that there is a grass. We are losing it by utilizing these hard labels. The next benchmarks, it's actually the Dino generalization capability, because they compared again with CLIP model and they compared the results on very specific data sets. And we can see that Dino is often much better. The same goes here. Those data sets are very specific, very hard. And we can see that Dino brings a lot of improvements. We can also check out the results for depth estimation and semantic segmentation with Dino as its foundational model, and it can be used across different tasks, which is pretty cool. So those foundational models, they are pretty inspiring. They took a lot of effort to train. They took a lot of data, compute. There are many more exciting models except for the Dino. We can check out the SAM, which is amazing. Segmentation out of the box. We can also check out the CLIP model. That is quite old, honestly. It was introduced more than 4 years ago, but this model actually has shifted this data science world from strict labels, because it was the model that was trying to match images with text, not with labels during training. And guys from NVIDIA got so inspired by all of these foundational models that they decided to try to merge capabilities of Dino, segment anything, and CLIP into one single model using knowledge distillation. So the main idea was to merge capabilities of large models into a single one and check whether the overlapping in knowledge that these models probably have will help the single distilled model in achieving better results. And they succeeded, actually. And what's really great about that paper is they not just created a model that was distilled from Sam, Clip, and Dino. They created a method that helps you to distill multiple different distinct models into a single one. And the student model is able to outperform all of the teachers on the representative benchmarks, and it still preserves the unique features of each of the teacher model, which is pretty amazing. So what challenges did they face? Of course, there is a mismatch in input resolutions across the teachers. There is a mismatch of output features dimensions across the teachers. And also there is a problem of fitting all teachers into a single GPU. And we will start with the mismatch in resolution and dimension problem. And they introduced adapter hats and integrated them into their pipeline. So adapter hat, it was receiving the super feature from the student model. And I call it a super feature because it's like a combination of all the teacher's features. And this adapter hat, it receives the super feature from the student and it transforms it in a way so that it will match a specific teacher that this adapter hat is attached to. So it means that we have the same number of adapter hats as the number of teachers. And the training pipeline is actually very elegant and simple. We have our input data. We feed it to our teachers, we receive some outputs from them, we feed it to our student model, which is trainable, and it's training to match teachers properly. We have the super feature from our student model, and we have this adapter hats that tries to transform the super feature from our student model to match the teacher, the specific teacher features. And those adapter hats, they are also trainable. It means that each iteration they learn how to match the specific teacher more. About the problem of fitting multiple models onto one single GPU, they actually didn't solve it. They were training on 64 GPUs. Half of the GPUs were working on Clip plus Dino task, and half of the GPUs were working for segmentation task, because segmentation task requires more memory. And also I should mention that there is a problem with knowledge distillation. The disadvantage of knowledge distillation is that you probably need to spend a lot of time on picking the best student. And they've tried a lot of models. They started with transformers, and transformers are really good. They're really good in segmentation tasks, but they require a lot of memory, which is a downside. They tried convolutional neural networks, which are actually very classical in computer vision and very popular, and they were very good in classification tasks. They are not that memory demanding, but they're not that good in segmentation tasks. And what they did, how they solved it, they came up with their own efficient architecture, which actually combines the best of both worlds, because they combined convolutional neural networks and transformers. They left most of the transformer architecture, but they added some convolutional layers at the beginning, because very good thing about convolutional layers, they actually allow you to reduce your data size. So they had those convolutional layers in the beginning, and they were reducing the size of the input data, and then that reduced size, they were feeding to transformers. And because of the downsampling of the data, transformers became not that memory demanding after all. And the best thing about convolutional layers, they're trainable. So each iteration, the model learns how to reduce the size of your image, but it learns also how to keep only the important information from the image, which is really cool. and they were able to reduce the attention cost of transformers, and they lose only a few % of accuracy on that segmentation task with their efficient approach. And of course, we will look into some benchmarks because it's very important. And here I want you to pay attention to, like, on the left we have the Dino and OpenClip compared to the efficient radio, and on the right we have SAM compared to radio. And I want you to keep your attention not only to the metrics, which are very good, you can see. Sometimes the efficient radio can even outperform the teacher model. But on the parameters count is basically your model size. And you can see that efficient radio 10 times smaller than Dino, but it keeps up with the accuracy. And same here, but you should pay attention to throughput. Throughput is basically how much frames your model can process in a single time. And you can see that efficient radio is a lot faster than segment anything, but it delivers a very good accuracy, sometimes even better than segment anything. And I think that the best thing about knowledge distillation and the best thing about that paper is that they took three amazingly huge models and they distilled them into a single one, and they were able to reduce the size of your model 10 times, but it still delivers the same accuracy as the teachers. It's really amazing. And in a summary, I think that knowledge distillation is relatively new. It was only introduced in 2013, but it has a really good potential even now because we are in the era of foundational models, and it really can help you in optimizing your model size. But yeah, be aware that you will probably spend some time on research and develop for knowledge distillation because you need to pick the right student. Yeah, that's it. Thank you for your attention. I will be really glad to answer all of your questions.
Well done. Questions? Starting off here.
Hello, and thank you for the talk. So I did write down the question, but so foundational models in your talk are not something that is that are text to image models, right? But you could potentially use different tools. For example, if you already have an image, you could, first like segment it, mask it, and then within the mask do some prompt engineering to change the image entirely. However, would you think it would make sense to somehow mash the possibilities of the foundational models, including their superpowers like segmentation, masking, and all other, to create a better performing text-to-image model in general? Because I guess it would make sense in a way to have a little bit more control with your prompts, to only create like a background and have already a mask for your the main shot of the image. But would you see it somehow in the future, or maybe it's already present, maybe with some these like models or companies that I'm not yet aware of, who are already implementing this type of infrastructure already?
Not sure that it's based on knowledge distillation, but there is a model called BERT. It's very popular in computer vision and NLP both because it is trained on 3 different losses, and loss is like a way that you are able to train your model. And this model is trained on 3 different tasks in parallel, like image matching, text generation for an image, and the third one, which I don't remember, sorry, but you can check it out. And it's not based on knowledge distillation, but BERT did utilize the knowledge distillation to create a better performing model because they distilled the original BERT into a smaller one. And also knowledge distillation can be used to this cross-model transfers from NLP to computer vision and vice versa, but I don't know the very popular papers right now. So I think it's something that we will see in the future.
Very nice. I saw some questions over here. Yeah.
Hello. Thank you for your speech. It was very nice, very interesting. I have a practical maybe question. How the accuracy of this model is measured? Are there specific tools or maybe some automated tests? How it is measured?
Yeah, there are a lot of popular benchmarks, as I told you. And those benchmarks, they are open sourced, and you can take any of it to test your model. And basically, when you submit a paper, you need to run the benchmark analysis to provide the results. So yeah, there are a lot of benchmarks. You can just pick any that is closer to your specific task and check the results on it.
All right. More questions?
Hello, thank you
Hi.
for your presentation. And maybe I just missed something, but I want to, if it's possible, can you highlight please the methods for the model distillations? I know backpropagation or whatever, something like that.
Yeah, backpropagation.
So it's basically backpropagation and that's it. No, I don't know, maybe parameters reduction or something like that.
No, they just use the classical the classical backpropagation, and they using some specific distillation losses, and they just backpropagate through the student to make it better, as in usual computer vision. Nothing new.
So it's no changes in the data. You just want to, how to say, update model. You just don't want to, I don't know, change data. It must be the same as for the teacher, and for the student it must be the same.
Yep.
Okay.
But you can apply augmentations to make it a bit different.
So it's possible, yeah, to change data for the student comparing to the teacher data.
Yeah, that's actually what they did in DINOv2, because they were applying different augmentations to the student and to the teacher. But that was not for the knowledge distillation to work. It was that they approach to fit different views of an image, of the same image, and have the same features from two models.
Oh, okay, thank you.
All right. More questions? Then I have one. I'm going to sit down. So for this teacher-student knowledge distillation, can you do that iteratively? Like, can students then also become teachers? Does that make sense to further reduce the size and up the accuracy?
No, it's always like one teacher
It's
and
a
one
one-on-one.
student. And usually in classical knowledge distillation, teacher is frozen all the way, and you're just training your student. But in Dino, they were just inspired, and they utilized some techniques of knowledge distillation in self-supervision. That is why they were training both models. But in classical knowledge distillation, you keep your teachers frozen because they are already good.
Yeah.
You don't need to train them.
Gotcha. Yeah. And with this, I mean, increased compute power with these large models, and especially with the distillation, we're trying to make smaller models, but it creates a lot of compute power. We have to compute a lot. You mentioned numerous amounts of GPUs, like it looked ridiculous.
Yeah, but
how
it's
is that?
knowledge distillation is something that you use when you serve your model to clients.
Yeah.
So that they are lighter. You don't need to pay a lot of money to cloud providers just to host your model, because you basically host it, hopefully for eternity of
Yeah.
your company existence. And that's technique that is used to optimize your inference, not your like training and research in field.
And you mentioned with knowledge distillation that you also might miss a part with the example that you said, okay, we're going to create a dog. You don't know anything about where the dog is running, or that it is running, or on what it is running.
It's not about knowledge. It's not only problem for knowledge distillation. It's something with the whole data science, the strict labels. They just lose a lot of information about your data samples, and that is why there is a talk that actually those labels prevents our model to learn more, because we only like describe in images or text in one word, but actually there are many words that can describe your data sample.
Gotcha.
And it's like a problem in data science.
Gotcha. Are there any more questions based on this? Otherwise, I'm going to sit down and fire off a few more. With Mary, our first speaker, she talked us through what we have in generative AI all the way up to agents, basically, recalculating whatever output they have, evaluating, and then reprompting. But we also mentioned that there is a lot of compute power. and there was a conversation of what happens with this compute power, because it's bad for the planet. Everything is kind of centralized in bigger data centers because we need that compute power in the first place. But where do you see this evolving when you have looked at large models and smaller models as well?
I think that right now, all these powerful players in data science like Meta, with Segmentinus and Dino and Llama, they are only aimed at creating these large models, because it's always about the data. The clearer your data, the better your model. The bigger data you have, the better your model will be. So it's always about data. So I think right now we will only see the big models.
And please correct me if I'm wrong, because I'm not that well aware of what it means to have models that are closed source versus open source. But what is your opinion on that specifically? Should the larger models that are foundational, be open sourced, that people can actually see?
That would be really nice for us.
That'd be nice, but it's not the case, right?
Actually, Dino is open sourced, so you can use it, and it's very simple to integrate Dino in your pipeline. We actually do it on my projects. We're using Dino out of the box. For RADIO, that is harder because you need to write a letter to NVIDIA and say why you need that model. But I think that these foundational models, they are very powerful, and transfer learning is especially useful and popular nowadays. So it would be really good if all foundational models will be open to us.
Gotcha.
To integrate them in our tasks.
Perfect.
And then I have one more question. What techniques do you also use for latency and cost optimization? So, for example, one way would be to use the knowledge distillation to reduce the model itself and maybe focus on a specific task. That alone would greatly reduce the cost for, let's say, GPU and I guess even the latency. But do you use any other tools, like, I don't know, for example, a very specific, let's say, format for which the model itself is being packed, or maybe some other like super secret spy stuff? And then the follow-up question: what would be the most suitable approach for serving such models on IoT devices?
Knowledge distillation is the answer to the second question. Yeah, but it requires a lot of research. And for the first one, in most cases we use quantization, because your model and the weights usually uses floating point, which requires a lot of memory. And when you quantize, you're actually transferring from float to int, and it requires less slots of memory, and that's how you can reduce the size of your model. For example, on one of my projects, we utilize in Llama 4 or 5 billion parameters, and it's just a huge model, and we are utilizing quantization, and we were able to reduce twice the model size, and instead of hosting it onto like 70 GPUs, we only use 30 right now.
Gotcha. Can you share with us a little bit about like the most fun project or the current project that you're working on with regards to computer vision? Because I'm really curious about that.
Yeah, I actually have one. I'm right now working on 3D segmentation, and we are utilizing Dino for not Dino, sorry. We are utilizing Segmentinus model. It's also a model from Meta, and we are utilizing depth estimation model, which I think also from Meta. It's 2 large foundational models, and we are using them just out of the box. And our approach is the following. The purpose of our project is to segment the utility poles that are placed around the streets. And the first thing in our pipeline is to remove the background, because as I showed you, segment anything model, it just segments everything on your image. And it's working pretty slow, plus you have a lot of masks, they are very big, and we don't need masks of our background. So we are using depth estimation that allows us to filter out the background, because usually we have the utility pole as a star of an image. So we use depth estimation to filter out the background. And then we apply segment anything model to produce the masks of the utility pole itself. And then we project these 2D masks into 3D space.
Nice.
I love computer vision.
Sounds really cool. Yeah. Are from the business side, are they aware of the costs involved in executing on this? Like, is that a conversation you need to have, or is that more of an afterthought?
Yeah, right now we are just proofing of a concept for our 3D segmentation, so we can allow ourselves to run models a bit more time, but of course then we will figure out how we can make them smaller. And actually, both segment anything and depth estimation, they provide a set of models in different sizes, and they use distillation techniques to make models smaller. So we will probably switch from bigger models to smaller ones.
Gotcha.
And you talking about that new project reminded me that there's this company in Vilnius. I'm pretty sure that you're aware of it, but I'm not entirely sure how they are named. But actually, they utilizes a lot of drones in their job. So, for example, one of the projects that they had, that they flew the drones around Vilnius city, and they basically were taking the photos of trash cans, whether to determine whether they are full or not. And if they are full, they would tell the company, company, that this part of the area needs to be taken care of. And that's only one of the projects. But what I wanted to point out, that there's a lot of, I guess, opportunities for computer vision, even just to make the city great, I guess.
Yeah, agree.
That's really cool. Are there any more questions based on the conversation so far? Otherwise, I'm going to round off with one question, because I work with the product team, specifically with software engineers, data engineers in there as well, and data science. And I've noticed that data science doesn't really mesh well with this sprint way of working, 2-week planning, retrospective as well. What is your way of working that you have experienced works well?
Okay, so usually when I receive a task, I try to understand what models I will utilize, and then I will go to Papers with Code. Is an amazing source of information for different tasks and for different models, and I will start from here. I will just try to pick the specific model which is open sourced, so I can use it. And I think in data science, right now we are aimed at transfer learning. It's when we use what is already exist from big companies, and then we can fine-tune it specifically on our data by introducing specific augmentations or introducing specific losses. But usually you always start with something that's already exists.
And it runs locally then, whenever you're experimenting, or do you run somewhere on the cloud?
On the cloud.
On the cloud, yeah, with regards to compute.
But actually, Dino's small one, which distilled from giant one, you can run it locally on your laptop on CPU, and it can give you prediction pretty fast, in a few seconds.